Okay, so so far we have introduced parallel computing and introduced supercomputing as example to show you, what are the hardware, software, or tuning that needs to be done in order to get the best of a computer system. Okay? And for the last part of this for this chapter 1 is to introduce the analysis tools for payroll program, right? How to measure the performance of a payroll program, how to analyze it mathematically, and also some of the performance metrics we commonly use for payroll computation. Okay, so the first performance metrics, also the most important one you must remember, is speed up factor. Okay, and the equation is quite simple, as you can see over here. The definition of a speed factor means the time of your program run it sequentially divided by the time of your program run it in parallel, right? So of course, usually the time run in parallel should be faster, right? So that means this factor should be larger than 1. But of course, it's not necessary or no, because in practice, in real world, anything could happen. Sometimes you use more computing power on higher parallelism, doesn't improve the or reduce the computation time at all. It could happen as well. Okay. But normally we should see a value, a result larger than 1. And of course, you can tell that the higher the better, right? Means that you get more speed up. Okay. And notice that the sequential time here supposedly should be the time you get from the best sequential algorithm, right? But however, in practice, it's hard to, you may not even know what's the best sequential algorithm, or it may be hard to implement one. Sometimes we just try to pick the best sequential code for evaluation. And for your homework, you are definitely going to measure it and plot the results to analyze your performance. And the way you can get the sequential result is quite simple, because your program's supposed to be able to run on n numbers of processor. So you can get the sequential result by setting n equal to 1, right? So your payroll program should definitely be able to run that sequentially as well. So you can just use the program you implemented to measure the time for sequential code and parallel code. Right? And the parallel time here, also you can see this speed up factor is a function of processor or your computing resources, right? So more resource you give it or more processor you use, supposedly you expect to get a higher speed up factor, right? So ideally, not hard to imagine, the plot you should see, expected to see, should be a linear line, right? If the x-axis is the number of processor and y-axis is the speed up factor you measure from the experiments, then as you have using more processor, you should get more speed up. And ideally, as you can imagine, if you use 2 processor, the time should be reduced by half. So this should be a linear line. However, in practice, as we said, there are many factors should be taken into account as well. Especially most of those things should slow down your execution, such as communication and synchronization we mentioned. And those overhead usually grows when the scale get even higher. So you will see the curve will actually bend down after, as you increasing the number of processor. At some point, it might become a flat line, and even worse, it could be goes down. right? It can go down either. So that's is what we normally see. For all those results, however, what you expect is those real measurements should be probably lower than the ideal linear line. And of course, if you can get closer to the linear line, the better. Okay. So if you fortunately get the linear line, that means you have a linear speed up. So that's the ideal case. And that should be the maximum speed up you can get, right, theoretically. And however, it is possible because anything is possible in life, so right? So it is also possible to get a super linear speed up. Means your speed up factor grows even faster, higher than the ideal linear speed up, right? That means like you use two machines and you speed up by 3 times faster. So how is that possible? Many reasons. One of them could be the hardware resource you get can bring you a lot more performance than you expected. For example, like memory, right? If you have more machine, usually means you have more memory as well. And if your problem size is small enough, then when the memory size is large enough, you probably can fit the whole problem, the whole data into the memory at once. So you avoid all the disk access. And as we all know, this access is much slower than the memory access. So by avoiding the disk access, you can probably double or even increase your performance by a lot, not just twice. Okay, so that's just an example, one of the example. So there are many other reasons and the factors could be taken into account, and that you observe a super linear increase. However, still is less likely to see, and especially when you get to higher scale, more number of processor, the line should always get smoother because of the overhead we mentioned that just will grow more and even exponentially over the scale. Okay. So although we like to use this term speed up factor, how much faster you get, right? But as you can see, this factor could keep increasing as you use more processors. So it's not normalized, right? This value could be if I say we have a speed up of 10, it has different meaning if you use just 10 machine or you use actually 100 machines. So you cannot tell the real fact from just this single value. So many people also like to use system efficiency. It's just a translation of speed up factor, write it in another way. As you can see, the only difference is the number you divided will multiply by the number of processor. So ideally, right, your value will be always less than 1. It should be between 0 and 1, unless you have super linear speed up. Okay, so it's a way to normalize the speed up by the amount of resources you use, and then at any case in any scale, you expect the best result will be 100%, right? So it's an efficiency. So it's another way to report your parallel performance, and it's a way that it's a measurement that is already get normalized. Okay, so for your homework, you're going to plot the speed up factor for your program, and of course you can also observe the system efficiency. And of course, for system efficiency, supposedly it will decrease, right, as the scale increased. Okay. All right. So in general, however, people still more often to use the term speed up factor, and system efficiency is lastly, that's often to be used. Some people call it payroll efficiency, other calls it speed up system efficiency. Speed up is more clear. Everybody knows when you talk about speed up, you try to record the performance when you add in more resource or when you do payroll computation. All right, and as we mentioned, right, the speed up result usually goes down when you have more processor because of those extra communication and computation, synchronization, all those issues reduce your speed up. Okay? How much, right? Theoretically, if you want to analyze it theoretically, how could we define or model the maximum speed up we could get from just analyze our code? So one way to see it is like we're showing here. We can usually we consider we divide the program into two parts. One part is the code that cannot be parallelized. For example, maybe the code for initialization, or the code for I/O, or the code that has race condition that cannot be run in parallel, right? And the rest of the part are the code that can be parallelized. So we use F to indicate the fraction of code that cannot be parallelized. So assuming the sequential time, right, is given as a base, we use TS to indicate that. Then you can see that, right, for a payroll program, F times TS is the part that, after we run it in parallel, it still has to run in sequential way. And the rest of the part, right, 1 minus F times TS, supposedly they can be perfectly parallel. And so the computation time, of course, will be evenly divided to the number of processor you use. So you get this right value below. Okay, so you add them together. That is your right time in parallel. So based on our definition for speed up factor, then you can do the computation and you can get this reduce it to this equation here. Okay. Okay. So what this equation, how it can be used for, or what does it mean? Okay. So what does it mean is what we stated before. A fact, is a result that we often observe in practice in real world. That is, if you can see that as you increase the number of processor, right, even so you fix the percentage of those non-parallel code. As the processor increase, your speed up curve will actually decrease, like we mentioned, right? And of course, if the part, right, the fraction of non-parallel code increase, right, for example, from 5% to 20%, right, your speed up factor will be even lower. So it's just an indication, show you this is a natural, right? This is a natural of our payroll code, because you cannot parallelize everything. So even without communication, even without other synchronization overhead, you still expect to see a curve like here below the linear speed up line. Okay, so you can imagine there are many other ways, right, to even model your computation time more in more detail, and so you can use those model, right, to guess or to analyze to show how your speed up factor may looks like. Okay. All right, so that's the first one. The most important thing, actually, we need to remember that speed up, the definition of a speed up, and why we measure speed up, and what we expect to see for speed up in the real world. Right. The next also very important thing is the concept of strong scalability and weak scalability. Okay. So those two are actually a way to measure the speed up factor. Okay. So actually the way to measure speed up factor can be strong or weak. So that means the way they measure speed up, the way they measure time are different. Okay. For strong scaling, that means when we try to plot the speed up factor, we need to increase the number of processors, right? So one way to do that is we only increase the number of processors without increasing the problem size. So for example, like your homework wants to implement a sorting algorithm. So the problem size is the number of items you're going to sort, right? So maybe the input you consider is the 100 element. So you measure its time, right? 100 element on one machine, two machine, four machine, etc. to plot the speed up factor we just mentioned. If you do it in that way, then you are doing a strong scaling experiments to get the speed up factor. Okay, so you can see the for strong scaling, its definition is the problem size cannot be changed in any scale. Okay, so of course the execution time should be lower and similar to what we saw before, right? And so again, if you your speed up factor grows linearly to the number of processor or core or machine, then that means you have achieved an ideal speed up under strong scaling test. Okay. So why is it strong scaling? Because when we compare to the weak scaling, you will see that for strong scaling, the amount of computation remain the same in each of the experiments, right, under any scale. However, the communication time, synchronization time, all those overheads supposed to grow, right, increase in the larger scale experiments. So it's harder to achieve ideal performance or achieve a better speed up results because those overhead will just keep increasing in larger scale. So strong because it's a number that's harder to achieve for any payroll program. Okay. So we have the weak scaling, as we will introduce later. It has an advantage that it's the same program, but sometimes it can show better result. So that's why for payroll program, when you see the experiment results, you definitely need to look more carefully whether it's a strong scaling result or weak scaling result, because they are quite different. So a program could have a very, very good, weak scaling result, but very bad strong scaling result at the same time. Okay, and however, of course, people do not invent weak scaling just to have a better number to show, right? That doesn't have any meaningful meaning to it. Okay, so the real reason people would like to consider weak scaling is, well, for two reasons. One, in some case, your problem size doesn't need to be fixed the same in a larger scale. You might increase it, right, just in your use scenario. So that's the scenario for weak scaling. So in some cases, in the scenario, the problem size could be increased in a larger scale. Second reason is it's harder to do strong scaling experiments. Why? Because the execution time will be affected by the scale, right? When you have more resources, your computation time will reduce. And as the time reduces, it comes with another problem. It's the noise, right? For example, if you run a program, a small problem, on a powerful supercomputer with 1,000 or 10,000 nodes, so you can finish it in 10 milliseconds. So that is very small, and it can easily affect by other constant overhead or something that's not related to your program at all, right? Those noise. So it becomes hard to validate or know the accuracy of your results. Okay, so sometimes we don't want the program run too fast as well. so we can ignore other noise factor in the experiments. Okay. However, if we want to make the time long enough for the largest scale in your experiments, then what happened when you try to get the result for a single core, right? The time will be huge, right? Because if you run 1 minute with 1,000 core, then it was only one core. You have to run 1,000 minutes. So that's a very, very long time. So sometimes we don't want to wait for so long for that, right? So it's a problem. As you change the scale, it's hard for you to control the execution time you prefer to have. So for larger scale, strong scale experiment, it's harder. You have to find a proper problem size that can fit for both the larger scale and the smallest scale. So that's an issue. Okay. All right. So for what's weak scaling, as we mentioned, right? Just as we just mentioned, different from strong scaling. If you're doing the weak scaling experiments, then what you can do is, and what you actually should do is, as you increase the number of processor or computing resources, you should increase the problem size proportionally. So in other words, in this experiment, you will fix the ratio, right, between the amount of computation and the a single core, right? The computation amount per processor will remain the same, no matter what's the scale you are conducting your experiments. Okay, it doesn't affect our speed up factor plots, because for any dot on this plot, right, like over here, for example, here 5 cores, still you run the program with the same problem size for for sequential code and for the parallel code. Okay, so the time, if you divide it, you should still expect to see the same definition for speed up factor. So it doesn't affect. But as we mentioned, different from strong scaling, every plot or every experiment you conduct here to measure the speed up, the problem size could be different. Okay, depends on the number of core. Okay. All right. So this is what we call the weak scaling, and it's weak because, in contrast to strong scaling, as we mentioned, it fixed the amount of computation per core or per processor. So that means when you have more processor, when you suffer from more communication and synchronization overhead, you can also spend more time on do the computation, right? So they can balance to each other, right? So not just the communication time increase, your computation time also increase. So the ratio between computation and communication can, ideally, right, remain the same. So his impact probably will remain the same. So you can expect your linear line, your speed up line, steadily increase instead of decrease. Okay. All right. So that's why it should be an easier situation for measuring speed up. So it's easier to achieve. That's why we call it weak scaling. Okay. And also you can see on the left-hand side, right, the execution time for the experiment you conducted under different core will, ideally, again, in a linear speed ups case, the execution time will remain the same. So you don't need to worry about the execution time on the different scale like we have for the strong scaling case. Okay, so it's much easier to pick problem size to conduct the experiments, right? So it's also easier to conduct weak scaling experiments. Okay. All right. So so that's why we have two definition, two way to measure the speed up. Okay, and for our homework, right, in our report, we will ask you to plot some of those results, and you are also more than welcome to plot both strong and weak, and to see what's the behavior of your program under those different scaling scenarios. Okay, right? So here is what I already mentioned, right? The difference between strong scaling and weak scaling, right? Because the problem size affect the amount of computation. Weak scaling, you can use that to balance the computation and communication ratio. So it's easier and easier to achieve better speed up results. That's why it's a weak scaling. Okay. Right. Okay. So lastly, we will talk about how to analyze the algorithm complexity for a parallel program, which you already have experiments, and you should have already know that how to do that for a sequential code. And now we will see how it will different, just slightly different for parallel program. Okay. So what's the difference? Most of the part is exactly the same. And I believe all of you already know how to analyze the algorithm complexity of sequential code, right? From your algorithm course. For parallel program, it only has two differences. The first one, because it's a parallel program, we not only analyze the computation time, we also need to analyze the communication time, right? Especially, it could be the main bottleneck under larger scale. So we definitely want to take that into consideration in our analysis. Okay, so you can see the time for a parallel program is divided by two parts: the time for communication and computation and communication. Okay, all right. And for the communication, this is the part you haven't heard from algorithm course, but it's pretty simple. For communication, of course, first of all, is you need to decide what's the model, right? The mathematical model to represent the communication time. And there could be many model exists. Some of them could be very complex, but normally, at least for this course, we use the simplest model as shown right here, right? That is to divide the communication time to the latency part and the bandwidth part, right? And the latency part, as we know, is right. Usually, it's a constant, right? You have a constant latency time when you initiate communication or when you try to send out a packet, right? So that's T star to indicate that constant delay for doing communication. And for the bandwidth, that's the data transfer time, right? So data transfer time can be computed by the amount of the number of items, right? The number of data item you want to send, and the time, the unit time, the time to transfer a unit data item, right? So that's, we probably all know already. So that's the simplest model, and we use that to analyze the communication time, at least for this course. Okay, and outside is Q, right? Q is the number of messages. So basically that means we are counting the total amount of computation time, communication time in your program by counting the number of messages you have to send out. And for each message, right, you need to pay a constant initialization time delay and the data transfer time. Depends on the network bandwidth and the amount of data items or size you need to transfer. Right. So of course, T star up and T data are all given. You only need to count the right? Number of messages and the number of data item in each message to analyze your communication time. And of course, then if you plot it in general, right, what you should expect to see is the communication time will looks like this, right? Okay, so that's how we measure or analyze the communication time. So for computation time, right, it's all the same, but the only difference is, of course, for sequential program, every instruction or every operation you try to count, they are executed in sequential way. So what you did is to count the number of operations. But here in parallel program, those operations could be executed in parallel at the same time, right? So if those operations can be executed at the same time, then we will just ignore them, right? So usually we try to find the slowest execution path and only count the computation along that path, right? All other operations, computations could be overlapped over time. So we can ignore that when we analyze the program. So that's why, of course, if you have better pair reason, higher pair reason, then more computation can be overlapped and can be reduced from your complexity analysis. So let's just use a simple example to check our definition and demonstrate how we could analyze a parallel program. Okay? So this is a very, very simple example, right? We simply have two computers, and each of them have some number or half of the numbers. And we want to say compute the sum of all those numbers across two computers. Okay, so what we could do, of course, there are many ways to implement this algorithm in parallel. And in this example, right, what we did is first of all the numbers we assumed it is only located at the computer 1. So computer 1 need to send half of the numbers to computer 2, so we can do those things in parallel, right? And after receiving the numbers, both computers can now try to calculate the partial sum of their local numbers, right? And of course, they have each have n divided by 2 numbers to add. And after you have the partial sum, computer 2 will send that result, that single value, that single integer back to computer 1. And the computer 1 simply add those 2 partial results together to get the final result. Okay. All right. So let's see how it can be analyzed. So first of all, as we mentioned, we will analyze it by the computation and communication separately. So usually the first thing is we will check what are the operations are communications, what are the operations are communications. And let's say we analyze the computation first, and that is step 2 and 4, right? Those are the 2 steps involve computing, not sending and receiving messages. Okay, and you all know, right? This complexity is just all of n, right? Although it's faster, but no, you don't see it seems looks like still same as the sequential code, but that's because we haven't take into account the number of processor yet. Okay, so so far it looks similar. Okay, for the communication, okay, you can see that that's step 1 and 3. So that means especially for step 1 and 3, each of them send out 1 message. Okay, so that's why Q equal to 1 for both steps. And you have the latency delay T stop up for each message. And for data transfer, it depends on number of element, right, you send. So for step 1, we actually send half of the numbers to computer 2. So that's n divided by 2. So it's a bigger size of message. But for step 3, we only send the partial result back. So it's a single integer, single data element. So we don't need to multiply anything to T data. So anyway, we add them together, and at the end, we will see the communication complexity is the same as computation. Okay. Okay, so this is how we analyze it. And if we treat the number of processor as a constant, then it looks like our complexity doesn't get reduced. It still remains at the O of n, and we need to pay that for both computation and communication. All right, so overall, of course, we just add those two together, and so the complexity remains at O of n. All right, so now make it more interesting to see how the impact of parallelism. So we generalize that solution to m processes, right, or m processor. Okay, and the idea is basically the same. Instead of divide the numbers to just two parts, we divide it to m parts now, and everything remains the same. And after step 1 and 2. Each processor now will send their partial sum back to processor 1 to do the sum of all the partial sums. And so we can do it in parallel with m processes. And analyze is the same, so we won't repeat that. But you can see the most important thing is now we have m in our equation. And obviously for step 1, the amount of data we need to send to each slave or each worker or each processes will now divided by m, right? It's n divided by m instead of just divided by 2. And the sending time, because it happened at the same time for all the sending for all the processes, so we only need to count it once. Okay. And for step 2, the partial sum. Again, instead of n divided by 2, now it's n divided by m minus 1, right? And also for sending the result, now for the master, right? Unfortunately, it has to receive m messages at the same time. Now here, because we assume you only receive one message at a time, so that's why we multiply it by m here. So he has to receive, because considering bandwidth is limited, then you actually have to receive them one by one. So here, when we analyze it, we assume receiving message need to be received sequentially. That's why we multiply by n. Okay, and finally, we have all the partial sum. So we have m minus 1 computation on the master node. Okay, so anyway, we just introduced m here, and again, we can follow the same way to add everything together and get the final result over here. And so what's interesting here is you can see for m, right, if it increase, it will actually, this part, it will increase the complexity. But for this part, m will reduce the complexity. So this reflects the nature of a parallel program, right? When you have more, when you have more processors or larger parallelism, the computation time usually can benefit from it, right? Like this part. But for the communication time, that's the other way. So it's always a balance between the two. So that's why it's not that trivial. What would be the best skill for running your program? So that's another reason why people usually like to plot those speed up results and to see when the curve will bend down and when the efficiency is lower than what we expected. So we could decide what would be maybe the best scale or the amount of resources we really want to spend on this computation. All right. Okay, so that's why some of the program has good scalability, while the others have pretty bad scalability. It all depends on your parallel program. So design and implement those parallel program is actually crucial, especially especially for communication time or synchronization. Those are overhead. Sometimes there are constant overhead that hidden in this this analysis. So the efficiency and the performance of parallel program, sometimes it cannot be seen clearly from this analysis because the constant overhead of those communication could be huge. Okay, but still we try to use this algorithm analysis to make sure your algorithm design are at least theoretically can be parallelized efficiently for probably both communication and computation. All right. So finally, now we know how to analyze the complexity of a parallel program, right? So for parallel program, we have this notion of cost optimal, okay, in terms of the algorithm complexity. And what it means is that if your parallel program, right, as you can see over here, if you complexity of your parallel program multiply the number of processor, right, equal to the complexity of your sequential code, then that means this is a cost optimal parallel program, right? Very much like speed up, right? Ideal speed up is your time proportional to your resource. Here is the same thing. If you can, in terms of the complexity analysis, your parallel program can grow or proportional to your sequential code, then it's optimal. Okay, so this is why we call if this happen, then your parallel program can claim to be a cost optimal algorithm or parallel algorithm. So the interesting thing here is let's see an example to see why this cost optimal algorithm sometimes can be misleading or different from what you were thinking. Okay, so let's just take a sorting algorithm as example. We all know the optimum complexity is n log n, right? So let's see. Let's say if you invent a parallel algorithm, right? It can use n processor and to reach all of log n complexity. Then this is a cost optimal algorithm, right? Obviously, and everything seems fine and normal. But however, it's very likely, and we will show this kind of parallel algorithm that use more processors. For example, n square processors, and achieve an ideal, the best, optimal, all one, a constant complexity. So you might think this is great, right? My parallel program has a constant complexity. But in fact, if you multiply those two together, you will see n squared is higher than n log n. So the other algorithm, the second algorithm, parallel algorithm, is not cost optimal. But if you just look at from the time aspect, you will think it's a better algorithm. Okay, so so you can see the complexity and the time. Sometimes they have they may show different results. It depends on which one you care more, right? In some case, the user, the programmer, really only care about is just the time. So they are willing to spend more resources and do the parallel computation less efficiently in order to achieve the best time. So this is actually a very interesting and strategy and useful strategy for reduce the time for a parallel program, right? Just try to use more resources, although it may be less efficient. Okay? And in many algorithms, it's very easy to do that, in fact, and we will see that in the third part, the second part of our course when we introduce different parallel program for different applications. Okay. All right. So so anyway, so for cost optimal, it doesn't care about the absolute time. All it cares about is the complexity point of view. Okay. All right. So this is it for our chapter 1. And as I mentioned, all the content in chapter 1 is really important because it teach you, let you know what is definition, right? And for parallel computing, and how we can classify those parallel, computers or parallel programming models, for those hardware software solution, how we can classify them, so we can know the natural or the definition or the behavior of those tools, or API, or those systems, in a general way, right? And of course, we use supercomputer to let you know how those hardware software can be further optimized, not just your code, to achieve better performance. And at the end, we introduce those uh, basic way to measure the performance and to analyze the performance. And of course, we will let you exercise that in your homework, in your report. And specifically, remember, in particularly, you should definitely clear about what's strong scalability and what is weak scalability. And so when you read those papers, read those other people's performance results, you will have a more better understanding to those numbers. Well, so you will be able to compare them more fairly and without misleading. Okay. All right, so that's it for the chapter 1, and it's also time for our class. So if you have any question, feel free to unmute yourself to ask your questions. Otherwise, you may log off now.